Hello. Here we're going to talk about the last couple of topics for Chapter 7. So these videos won't be too long. Our first topic is ionization energies, and this is another property of atoms that we can look at to understand the trends in the periodic table. But first, let's define what an ionization energy is. Ionization energy is taking an atom, we'll just use a generic atom M here, and ionization energies are specifically defined for the gas phase. For most elements, they don't exist in the gas phase, but you can make them into the gas phase with enough energy or heat and measure these ionization energies. And so it's how much energy does it take, you have to input energy somehow, to knock off an electron. So you form the positive, the singly positive ion and an electron. And so that is what's known as the first ionization energy. And then we can keep doing that. So first ionization energy is often written as IE1, and it refers to this reaction here. You can think of it as a reaction. And then our second ionization energy is you then put in some more energy, and you knock off a second electron. You form the 2+ ion. Again, all in the gas phase. So this would be IE2, or the second ionization energy. Now, we can look at properties of these ionization energies for different elements. And one thing about this is that we can find evidence for these different orbitals and shells and subshells that we're talking about from these ionization energies. We can see there are clear differences in how much energy it takes to remove electrons from different kinds of atoms. Now, these are always an input of energy. These are always an endothermic process. We have to put in energy to get the electron to come off because we have the positive nucleus. And even if the electron is, all the way on the valence, right, we have our core electrons here, and we have this valence electron out here, it's still being pulled on by the positive nucleus, and so we have to input energy to get this electron to come off. And so this is what we call the ionization energy. Now, in the periodic table, there are some trends that we can observe in first ionization energy. So if we look at IE1, we can look at the trend as we go down the periodic table. So as we go from top to bottom, similar to, we can think about this in terms of similar to the size of an atom. As we go down the table, N gets bigger, and so the electrons are further away from the nucleus on average, and so it's easier to take off that electron. So as we go down the periodic table, ionization energy decreases, meaning it's easier to take off the electron. So if we have something like hydrogen, that electron is held very close in a 1s orbital, right? So if we have hydrogen, its electron configuration is 1s1. And if we think about our electron here in this orbital around the nucleus, it takes a lot of energy to pull that electron away. Whereas if we go down the periodic table all the way down to something like cesium, now our electron configuration is, we're going to have our core electrons, and make sure I get the right element here, xenon, as all of our core electrons. So there's a bunch of electrons in here shielding the nucleus, even though we have a very positive nucleus. And then we have a 6s1 electron. And so our nucleus is here, but our 6s1 electron is all the way out here, right? This, on average, it's very far from the nucleus. So that orbital has become much bigger. It takes a lot less energy to pull off this electron from cesium. And the same trend is going to occur in other columns of the periodic table. I just picked the first column because it's the first one. So that's our trend in ionization energy as we go down the periodic table. Again, similar to size, we can look at as we go left to right across the periodic table. So as we go left to right, I want you to pause and see if you can predict what the trend is. All right, so hopefully you paused and thought about this. So as we go left to right across the periodic table, the effective nuclear charge increases, and this is what causes our atoms to get smaller as we go left to right across the periodic table. That means they're pulling tighter on the electrons, and it's harder to get off the electron. So the ionization energy increases as we go left to right across the periodic table. For the exact same reasons that the atoms tend to have the trend of getting smaller as we go left to right across the periodic table. So that's a clear trend that we can see. One way of visualizing this is this figure from your textbook that has some actual data on this. Let me pull this over. I need to exit full screen for a second so I can make this bigger so you can actually see it. So here's some data on ionization energy, and these are all first ionization energies. So we're always just pulling off one electron in these. We'll talk about second and third and et cetera ionization energies as we go forward. But we can see this trend. So here, this figure on the left here, we're looking at ionization energy on the y-axis and atomic number on the x-axis, looking at Z. And so we can see these peaks here in the ionization energy that all correspond to noble gases. Noble gases have a very stable electron configuration. Their electrons are held much tighter because their shells are all full, and so they have the highest ionization energies as we go left to right across the table. Now there are a couple of things that you may, it's not a direct trend. So there are a couple of spots where we see, for example, going from beryllium to boron. What's happening here is that we're adding an electron to a new subshell. So, boron, we're looking at the electron configuration of helium, and we have a 2s2, 2p1, and it's preferred to just have an empty subshell. So taking this electron off is actually a little bit easier than you might expect because you are left with an empty subshell. And the same thing happens between nitrogen and oxygen here, where we get this little dip. We go from a 2p4 in oxygen. Let me make sure I have that right. Yeah, 2p4 in oxygen. Those are our valence electrons. You also, of course, have the s electrons as well. And if we lose an electron, we end up with a half-filled shell. So this would be O+. This is half-filled, and that's a little bit more stable, and so it takes a little bit less energy to take off that electron because you're left with something that has a little bit lower energy. But in general, we do see the trend that we said, left to right, we go up. And as we go down the periodic table, these are, as we get to higher and higher atomic numbers, the ionization energy is decreasing as we go top to bottom. One other thing we can look at is ionization energies for higher ionization energies. And this can give us evidence of subshells and things like that. So again, grabbing some data, if we look at the ionization energy, we'll just look at hydrogen and helium to start with. So ionization, and we're going to look at ionization energy 1 versus ionization energy 2. Now, of course, for hydrogen, there is no ionization energy 2. So the first one, and these are all in kilojoules per mole. So this is how much energy it takes per mole of atoms. So ionization energy 1 for hydrogen is 1,312, whereas for helium, it takes a lot more energy to pull off an electron because we now have 2 protons, and ionization energy 2 increases by quite a bit, right? Because we have a full subshell, and it's a lot. You're disrupting this very stable configuration, and so you tend to, when you have a noble gas configuration, that ionization energy to break up that noble gas configuration will be a very high ionization energy. So going one further down the periodic table, lithium, the first ionization decreases a lot. So this is an example of that trend that as we go down the periodic table, so lithium's right underneath hydrogen, we have a drastic decrease in ionization energy because now we're looking at 2s electrons versus 1s electrons. So here we're removing a 2s electron, but we can remove another electron. But our next ionization energy goes up by a whole lot, 7,296 kilojoules per mole. And what's happening here is we've already moved the valence electron, and now we're removing core electrons. This has to be a 1s electron that gets removed, and so that takes a lot more energy when you're getting into those core electrons. We can see similar trends if we keep going to beryllium. Ionization energy 1 is 900 kilojoules per mole. So again, we're seeing that trend left to right across the periodic table, and ionization energy increases because effective nuclear charge increases. Ionization energy 2 is larger. It's harder to take off that second electron because you have this positively charged nucleus that's holding onto it, but it's not crazy high. But if we look at ionization energy 3, so we've removed all the valence electrons, and now we're looking at the core electrons. So this electron was a 2s electron, this electron removed was a 2s electron. And now we're looking at 1s electrons again. The ionization energy jumps up to 15,050. So a huge increase in the ionization energy. And again, this is because now we're removing core electrons. And this is evidence for these shells and subshells that we've been talking about, that all this quantum mechanical stuff, all these orbitals, really do exist and are reflected in data that we can measure about the atoms. So we could look at this for additional elements, but the key idea here being that if you're removing electrons, basically removing core electrons is really hard. And it takes a lot of extra energy to do that. So that concludes our video here about ionization energy. In the next video, we'll talk about one more periodic trend for atoms, and that's looking at electron affinities, which is adding electrons to elements instead of taking them away.